Hi, I'm Girish from the Electrical Engineering Department at Columbia University, and today I'm speaking about a heart rate monitor I designed as part of the E6350 course, VLSI Design Laboratory, offered by Professor Peter Kingett in spring 2015. I was helped in this design by Olivia Jin, who's not with me right now. Now I'll discuss the principle of a PPG. So PPG stands for photoplethysmograph. Plethysmograph is a general name given for an instrument which measures volumetric changes in certain organs. Specifically, a photoplethysmograph does this by shining light through a certain part of the body and either looking at the transmittance of the light through this part of the body or looking at how the light reflects from that part of the body. So, in the context of measuring heart rate, how this is achieved is that the light which is transmitted through a finger, for instance, can is modulated by the blood flow through the arteries and veins in that finger. Since the blood flow through the blood vessels is synchronous with the heart rate itself, thus the signal received by the phototransistor contains information about the heart rate. I will now go through the implementation details for the heart rate monitor as well as the respiratory rate monitor. So this is the block diagram for the filter chain used to filter and amplify the raw signal from the PPG sensor. It consists of four stages. There are three filtering stages: the first, the second, and the fourth stage. The third stage is flat and it is just used for providing programmable gain to the filter. The first stage performs some high-pass filtering to filter out the intrinsic DC point of the PPG sensor, and it also does some low-pass filtering to get rid of high-frequency components. The second stage is a high-pass silent key stage with gain. The fourth stage is a low-pass unity gain silent key, and the third stage is just op-amp in a non-inverting configuration to give gain. The OTAs are realized on-chip on a 180 nanometer CMOS process, while the passive components are realized off-chip. The reason the passive components need to be realized off-chip are they are fairly huge because the filtering frequencies you are concerned with over here are commensurate with that of the heart rate, which is roughly 1 Hz. These components cannot be realized on-chip easily. The respiratory rate monitor has a similar topology, and the only difference between the respiratory rate monitor and the heart rate monitor is the value of these RC components, since the passband of the respiratory rate monitor has to be of the order of around 0.1 Hz for breathing rates of around 5 to 6 breaths per minute. This is the board we use to test our chip. So there are two instances of chip. One instance is for the heart rate measurement and the other instance is for the respiratory rate measurement. So the sensor is interfaced to the board through a DB9 connector, and that signal is fed into both the chips. And there are a bunch of potentiometers for setting the bias as well as to set variable gain. So the output from these two chips, there are two outputs from each of these chips. One is the raw analog output of the filter chain, and the other is the digital output which is the analog output which is passed through a comparator. And both of these are fed into an Arduino Uno, which is interfaced with this board. And the Arduino Uno drives an LCD display which determines the heart rate which is captured by the sensor. We also have a bunch of indicator LEDs which blink on and off at the heart rate and at the respiratory rate respectively. So right now the LCD reads a heart rate of around 90 beats per minute and the respiratory rate of around 7 breaths per minute. Now I'm probing certain signals of interest from the board. So I'm primarily probing three signals right now. The signal from the PPG sensor, the signal out of the filter chain, and the digitized signal from the comparator. So these are what the signals look like on the oscilloscope. and as usual, they're terrible. So the blue signal is the signal from the output of the filter chain. The yellow signal is the digitized output from the comparator, and the green signal we can see here, it's fairly weak, and the green signal is the output from the PPG sensor. First and foremost, I'd like to thank Oliver. This project is a culmination of both of our efforts, although he isn't around today. I would like to thank Moses for giving us an opportunity to tape out in their process. I would also like to thank the E department for funding the fabrication of our PCBs and for the components. I would like to thank Professor Peter Kinget for having offered this course and for his guidance throughout the course. I would like to thank the TAs, Daniel and Sarthak, for having invested their precious time. And I would also like to thank Fungchi. He was an immense help in making this video. I couldn't have done it without him as well.